Hi, this is worksheet 2, an extended version. And what we'll do is we will look at the answers for each of the problems, make sure you did everything right. But first, what we'll do is we'll look at the first set of problems given a unique Ka, Kb, and Ha. Now, the first thing you're going to have to do is solve for the Ka. Now, the Ka for the first one is solved using the equations that you were given, and there's Ha and Kb, and so you would use the values to calculate the Ka, and the first one we'll do is E, the estimation, and then we'll do Q using the quadratic or the exact value. Now, starting the estimation, what we'll do is there's the equation, and then we'll solve for Kb. There's Kb dividing through by Kb, we'll get Ka. There's the equation for Ka. Dividing 1 times 10 to the negative 14th by Kb, we get Ka. Next, we'll use the Ka to determine the value for H plus. Now, we know in terms of the estimation that HA is going to be 0.1. Now, that's the molarity of the HA solution. For every one of H plus 1 produced, I'll have 1 of A minus produced. So the value for H plus we're looking for will be the same as the value for A minus, and that will be X. So H plus 1 will be X, and A minus 1 will also be X. Now, let's be clear. The HA is only partially soluble. Now, how do you know that? Well, look at the Ka. The Ka is approaching 0. It's very, 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 very small. Because it's small, you have a weak acid. So there is the expression for the HA. You have HA is 0.1, and then correspondingly you have the H plus and the A minus, correct? And as a result of that, you're going to have you're going to be able to set up the dissociation constant, the expression for that, which is given as Ka yields x squared over HA. So now we're going to plug into the expression and then grind it out, and you're just simply going to cross multiply and then take the square root of both sides, and the answer is 1.5486 times 10 to the negative 3, and that's the H ion concentration. Remember, we were solving for X. Now, the OH concentration is given in terms of the expression for Kw, as we see here. Now we are going to plug into the Kw expression, solve for the OH concentration, and at 6.4575 times 10 to the negative 12th, we'll take that value and plug into the equation to solve for the pOH, which is the negative log of the OH concentration. See the brackets around that, that's the molar concentration. And then we plug into that equation and we come up with 11.1899. And that's going to be the pOH. Now we're going to take that pOH and we're going to plug that into the equation, which says that the sum of the pOH and the pH equals 14. Using that equation, rearranging it for the pH, we plug in and we find that the pH will equal 2.8101. So you can see that it's a very acidic solution. Now let's look at the quadratic equation application for the exact amount. Here's the Ka times Kb yields 1 times 10 to the negative 14. This is something that you saw earlier. We're plugging into the expression above, and we're generating the Ka, which is 2.3981 times 10 to the negative fifth. Again, this is repetitive relative to what we saw earlier. Now, we take that Ka, and now we're going to use the same equation. HA yields H plus and A minus. However, the difference is going to be this. As the HA dissociates into H plus and A minus, forming X H plus and X A minus, you have to subtract off that portion of the HA that's dissociating. For instance, if it were a strong acid, HA would completely disappear slowly or fast, and it would turn into all of H plus and A minus. But this is a weak acid. But some of the HA will disappear. So you have to take that into account. So it's going to be 0.1 minus X. Now, we're here in doing this to see whether or not that's a significant amount compared to the estimated value. And this is the basis of the quadratic equation that formulates as a result of this technique. There's the X for H plus and the X for A minus. This is the dissociation expression. Plug in the values for HA, H plus, and A minus, and then run through some basic algebra to simplify the expression, which makes the quadratic equation obvious. Now we're going to set that equal to 0. We're finding the roots, so to speak. That's going to be A is 1, B is 2.3981 times 10 to the negative fifth, and C, notice, is negative 2.3981 times 10 to the negative sixth. Now we're going to use the quadratic formula to set that equal to X. That's what we're solving for. But notice that there's a problem with that, and that is the discriminant must be positive, because the molarity is a scalar quantity. Discriminant must be positive because molarity is a scalar quantity and has a quote-unquote positive sign. I'll explain a little bit more about what that means during class. However, suffice it to say that X has to be quote-unquote positive. Now, let's change that to positive, and let's begin to plug in. We have, first we plug in B, and then we're going to plug in B again under the discriminant, and we're going to square that eventually. And then we're going to plug in A. Notice it's minus 4AC, and we're going to plug in A, and then we're going to plug in C. Now, notice that C is negative, and what will that do to that term for AC? But it will turn it positive. Now we're going to plug in A below, and we're going to carry that to the next slide. Now make sure that you do this very carefully. Make sure that you don't drop a negative or add a positive, and then do the numerator separately from the denominator. And then don't write down the rounded value for the numerator. Just keep it in your calculator and divide it by 2, and that's going to equal X. Notice we have X is going to be 0.0015366. We carried it out several decimal places because we want to actually compare the values for the estimated and the more accurate value. Notice that the X is the H plus. Now we're going to solve that expression, the KW expression, and we're going to plug in the H plus to solve for the OH negative, apply some basic algebra, rearrange the equation, and we find that the OH negative is going to be 6.5079 times 10 to the negative 12th. And that's, of course, the molarity of the OH. Now we're going to take the OH and we're going to apply the equation to find the pOH. The pOH equals the negative log of the OH negative concentration, and then that's going to be, the pOH is going to be 11.1866. Now we're going to apply the expression where you have pOH plus pH equals 14, and that value for the pH is going to be 14 minus 11.1866, and that's going to be 2.8134 for the pH. Now for the results, so that we can look at everything to see whether or not the two methods are significant. Do we have to always apply? Now remember, the Ka and Kb are very small. Look at the Kb, how small that is. The question is it important to employ the quadratic formula with the exact answer, where you have the 0.1 minus x, or can I just use the estimation to get a fair value? You can see that the Ka is 2.3981 times 10 to the negative fifth, and Kb is 4.17 times 10 to the negative 10th. But what does that really mean when it comes to understanding the size of these numbers and whether or not it's significant to subtract x from the beginning molarity of the acid? Let's take a look at place value. Kb above the top one is 0.000000000417. I think I said that right. And Ka is 0.00002398. And you can see the place values are going to be listed as follows. It's going to be ones, and then the decimal point, and then tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billionths, 10 billionths, 100 billionths, and trillionths. So you can see that these numbers are very, very, very small. So how do you actually write the name of these numbers if you were going to write the names of them? Well, the Kb would be 417 trillionths, truly a very small number. And the Ka is also very small, would be 23,981 billionths. So these numbers are both very small, so it's doubtful whether or not the values between the estimated and the accurate would be terribly dissimilar. They probably would be very similar, and the estimated value would probably be fine for our purposes anyway. So let's look at the values as they are listed and see if we can draw some conclusions. So there's the H plus ion, very, very similar. If we rounded it to, for instance, in this particular case, thousandths place, you would get a very, very small difference. It'd be essentially the same, etc. So those are the values, and it's obvious that the quadratic equation is not necessarily needed unless it's otherwise stated that it would be important to use the quadratic formula. And for biological purposes where enzymes are involved, that it's very, 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 very small trillionth of a particle might be very, very important. But for our purposes relative to practicing how to do these equations and problems, the estimated value would probably be more than sufficient for our purposes. All right, let's start this where we kind of left off at the beginning before I was showing you how to do it specifically. And what I'll do is I'll just let this run, and I will uncover the answers as we go. And that finishes my portion of the lecture. And just make sure you put it on pause when you need to so that you can work out the problems before they appear. I'm only going to have it on 3 seconds per slide, not even. So they'll go fairly quickly through here. So good luck, and make sure you go through as many of these as you can until it becomes very, very much second nature. Okay? And have a good day, and goodbye. This is an extension of the worksheet 2 that you did for homework. This is 6 through 10. The worksheet that you had to do was 1 through 5, so this is additional practice for you. Okay, and then at the end of this worksheet, there's going to be worksheet 1 is going to be done. So you can check your answers on worksheet 1 and on this particular extension. So you can you can do this, but try to do these yourself before the answer is revealed.